on the vertex stuff, and so please.
All right. So okay. So before I forget again, let me tell you a little bit the connection with some of the things that. Well, I don't know the connection or the coincidence, perhaps, with some of the things that Damian was saying, but in a much more pedestrian way. So, in classical mechanics, I was thinking of Poisson algebras. We had Lie aneroids. And I'm not sure how to put a name here, so most probably this number is going to be wrong, but I will think on symplectic 1 minute.
Well, I mean, this is known stuff to physicists.
I understand, but the number 1 some people might like it to be a 2.
I mean, look, this is physics institute, so physicists are dominating.
So, okay, so
let me make this
this is like 1?
So,
what's the number that this is like?
1.
1. Okay, good. Then I'm happy. Then I got it right.
Yeah.
Okay, so then
it's a physics institute. Don't forget it.
No, good. It's just that I don't know which numbers people like better. So instead of Poisson algebra, now I can think of a Poisson vertex algebra. Vertex algebra.
And it's number 2 there.
Exactly. This is going to be a symplectic 2 manifold. 2 manifold.
And this is Reutenberg work.
And well, no, Reutenberg's work is here in the middle, where I got to current algebras. Actually, I should be really careful because from Poisson vertex algebras I got into current Dorfman algebras, which is also Reutenberg's work. So perhaps you can ask yourself, what is the geometry behind current Dorfman algebras? I don't care about this question now, but what is true is that out of a current algebra, or a Poisson vertex algebra with this non-degenerate pairing, I can build this symplectic 2 manifold. Now, there's a procedure that produces you an action for a topological field theory. Whenever you give me a symplectic K manifold, which is this KKZ business that was mentioned many times. But then, to a symplectic 2 manifold, then I should be mapping from 3 manifolds, not from 2 manifolds. And somehow, this was some vertex algebra business that I constructed. And the vertex algebra quantization that I'm doing, this has to do with 1 manifold. This was classical mechanics. And this has to do with 2 manifolds. So I think it's interesting to study this mismatch between, I am going to construct now something that I'm calling a quantum theory, but it's essentially in dimension 2.
There is no mismatch. I mean, once part of the story well studied, there is a very well understood relation between Chen-Simons and Vezuminovitz model. So that's example.
Yes.
Then they should hold beyond the things, but nobody studied it. I mean,
correct. So there should be a relation like this between a 3-dimensional TFT that this side is supposed to produce me, and a 2-dimensional CFT that this side is going to produce me. But then the question is, what's beyond this? You guys have studied this thing very well. So how about this column? Can you tell me what's beyond this column? Okay. So this is how these things are connected to what we've been here. But let me tell you how to quantize these guys here. But I'll be much more down to earth, and I'll quantize the trivial current algebra. Okay? So I told you already that there are subtractions. I mean, this is the part of the talk where I told you I want to sell work of Malikov. I mean, given this talk, we don't mention it, this is stupid. Malikov, Sheckman, and Weintraub. This is, Weintraub is probably like this. Chiral rank complex. So, Weintraub, I read the paper in Townsend lines and I still don't get Townsend spells. Alright, so, okay. I'm gonna be very precise in this. Remember that my problem to quantization was this statement. If I take the beta gamma system and I look at this fails to be zero. So there's no way that I'm going to describe you anything in terms of vector bundles on a manifold. So what they propose to do is to glue a free field theory on patches in a manifold. So what Domenico, Sheckman, and Alberto did is as follows. Is first of all, you can't. So first observation. First observation. There are topological obstructions. Obstructions. To quantize. The Poisson vertex algebra associated to the standard Courant algebra on a menu. There's a characteristic class that classifies this, and if this guy doesn't vanish, then you don't have quantizations. Let me make a proper statement, but I'm not going to write it. So the statement is as follows. Quantizations, so let me one statement. This Poisson vertex algebra was generated in degree 0 and degree 1. If you exercise, grab the actions that I gave you of a vertex algebra, and what is a vertex algebra in degree 0 and 1. You'll find a bunch of actions. But now whatever is sitting on degree 1 is no longer a module for whatever is sitting in degree 0 because of the lack of associativity. So the answer to this question, whatever this bunch of actions is called a vertex algebra. And statement 1, that this I'm not going to write. If you manage to quantize the Poisson stuff into this guy, just in degree 0 and 1, then you don't have more obstruction to quantize the rest. So if you manage to quantize a theory that is freely generated in degree 0 and 1 to degree 0 and 1, then there's no obstruction in quantizing the rest. This statement 2. Quantizations in degree 0 and 1, if there exists one, there exist infinitely many of them, and they form what is called a Ger. They're a transitive space for certain group. The problem is that there's no canonical one, if there exists one. And statement 3, there might not exist one. So this is as much as I'll say without writing. So instead of solving this and getting into the subtle questions, which are the topological abstractions, to this guy being quantizable, I'll just brutally add a lot of supersymmetry so that I can quantize this thing. So instead of looking at maps from S1 into the manifold X, so the loop space of X, I'm going to be looking at maps from a super manifold, S11 into X. So instead of the beta gamma system, I'll be looking at the BC beta gamma system. So let me tell you what that is. So this is a super vertex algebra. So exercise. You can find in the notes a proper definition, but a super vertex algebra is exactly what I defined. It's just that whenever you commute two things that are odd, so this is a graded vector space, an even part and an odd part, and whenever you commute two things that are odd, you need to add a -1 in all of the actions. If you commute two things that are odd, you just add a -1 in front. So for example, to give you one axiom, AB minus BA, this was the integral of A lambda B, B lambda between this and this. So now here, if the two guys are odd, you will put a -1. And if the two guys are even, you will put a +1. So things anti-commute or commute. So the BC beta gamma system is a super vertex algebra generated by the following lambda brackets. Beta gamma is equal to 1, which is B and C. The only difference is that these guys are bosons, so these are even, and these guys are odd. So lambda, gamma beta is equal to -1, whether C and B is equal to +1. Okay, so let me add a little bit of supersymmetry then to the whole picture. So I'll be brutal first. Okay, so I want to construct first a Poisson vertex algebra, and then that has this feature locally on a manifold. I want it to be some sort of a BC beta gamma system. So what you'll do is the following. So choose I'm going to do this in coordinates. You can certainly do this without coordinates, but I think this should be a down-to-earth question class. So choose an open U with coordinates gamma I on your manifold X. Okay? So now, in this open set, I will give you to this open set, I'll attach a vertex algebra, VU, which is going to be that free boson system. So this is the beta gamma system, now with brackets, non-trivial brackets, pi lambda gamma j is equal to bi lambda cj delta ij. So as a mnemonics for this, I'm going to be thinking on these gamma i's as coordinates. I'll change this label in a second, but I'll be thinking in this way. These guys I'll be thinking as differential forms, d gamma i's. These guys I'll be thinking as vector fields. And this guy here I'll also be thinking as vector fields. I'll change this in a second. Okay, so now I want to glue this theory in a different patch. I have a free field theory on the patch U, and I want to glue this to another free field theory on the patch U tilde, where I have also my fields, beta tilde I, gamma tilde I, C tilde I, and B tilde I. So what do I need to check? I need to check that these fields change coordinates in a nice way so that the OPEs between them on the intersection, these two vertex algebras agree. So this is only I need to check. If these two free field theories agree on the intersection, I'm done. So for this I need to express the new fields in terms of the old fields. So of course I know already. So if I make a change of coordinates, gamma i's are just functions of the gammas. There's nothing I need to do. Since the gammas commute among themselves, the lambda brackets between the gamma tildes and the gamma tildes is still 0. So that was fine.
So this is now quantum or classical?
Sorry?
This is quantum or Poisson?
Oh, good. Choose one. I'll do this the quantum directly, but the answer is the same. I could have told you Poisson and it's the same answer because at degree 0 and 1 they're essentially the same. There's going to be one subtlety in the quantum level that I will point out in a second.
But even on the classical level, you need to do it locally and then do without a global description.
I can give you a global statement at the classical level. So I constructed for any current algebra a Poisson vertex algebra. Okay? So for any manifold X and a current algebra over X, I constructed a Poisson vertex algebra. So do the following. Take T1, T star 1 of X. So this is a super manifold. So let's call this guy Y. And let's take the standard current algebra here, A of Y. So we have the Poisson vertex algebra here like this, and push it down to X. So this is a Poisson vertex algebra on X. That's it. This is what I'm quantizing now. So this is a way of producing this without giving you any. So these are like differential operators, but not to X, but to the T star 1, or X the RAM, essentially. But the problem is that doing this at the quantum level, I cannot really do this coordinate independent way unless I go to superfields. And I don't want to talk about superfields. Alright. So these guys will commute at the quantum level as well. Because the gammas commute, and that's it. Now I need to tell you how the B's and the C's change. Well, I just told you. C tilde I is just del gamma tilde I over there gamma j, Cj. And now I check. I mean, these guys commute with this and they commute with the C, so the lambda bracket between this and this is still 0, so it's fine. And two of these guys commute because the gammas commute with gammas and the C's commute with C. So there's no problem so far. So let's go to the B's. The B's are going to change as vector fields. B tilde I is just off. I'm very bad at this. These are much better than me on this. So I'm sure there should be a gamma tilde on the bottom. And now let's suppose I'm going to put a J there, and here's the question. I think I'm going to put a J here. Tell me that I got this right.
No.
I'm horrible. Thank you. Okay, but then again, so this and this still commute by the same reason, and now I need to check how these two guys commute. And here I need to be careful, because the algebra is non-associative and non-commutative. So I need to apply the Leibniz rule. But notice that the Leibniz rule won't produce any problems, because the only thing that doesn't commute here and here is this C's and this P's. Right? So exercise, check by just one application of the Leibniz rule that the lambda bracket of B tilde I lambda C tilde J, I should probably do this and give the other ones an exercise. But I said that I wasn't going to do more computations. This is a trivial exercise. It's that I. There's no problems with the quantum stuff. You see, when you contract these two guys, you get a delta ij, and this contracts these two derivatives, and this is the delta ij. So, okay, so far so we're good. The biggest problem comes with the other thing, and this is what essentially the big part of the paper of Malik and Weintraub and Sheckman is that if you do the naive thing for the betas, you find a mistake. So let's do beta I to be beta tilde I. Beta tilde I to be the derivative of gamma j del gamma tilde I beta j. And I want to check that how this guy commutes with itself. This is the biggest problem. This with the gamma is not that much of a problem, but I need that beta I, two vector fields beta I and beta j should commute if I want to get the same verticality. And beta I with beta j here, they won't. And the essential problem is that when you're applying the Leibniz rule, if you have two of these guys, two quadratic terms like this, so you have some gamma beta, this guy doesn't commute with this guy. And this guy doesn't commute with this guy. So in the integral term, in the weak form, you're going to pick up a lambda square term. So you need to solve for the problem that this beta I, beta j is not 0. And the way to solve for this is by adding a corrective term. In the language of, so Nekrasov did this in a different way by passing to the first order formalism in the action. Tilde I, del gamma tilde j, so this is del squared j, or probably it's k. Here is a del, so this is gamma tilde k, and here's an m, and here I got, oops, not I, I'm calling this cm b I, bj. And moreover, I need to be very, very careful because this algebra is non-associative. So everything here doesn't need a parenthesis. They commute among themselves. But the C's and the B's don't commute. So I need to tell you how to multiply these guys. And I'm telling you here, first take the normally ordered product of these two guys, and then take the normally ordered product of these two guys. So exercise. So this is the grandiose thing about these guys. If I put this horrible transition of coordinates, I'll give you two exercises. One is that beta tilde I, lambda, beta tilde j. This should be easier than the computation that we did already for the beta solid. Is 0. Therefore, these two vertex algebras glue nicely. But the exercise 2 is that try to think on this manifold that I of course just erased, on T star 1x. Here we have coordinates gammas. Here we have coordinates that are just vector fields on x. Vector fields on x are going to be odd, even odd coordinates for this manifold. So here we have some coordinates that are d by d gamma I. So how about in this manifold that I'm calling y, think on the tangent bundle to y. Or probably you want to put sort of like the tangent bundle shifted by 2 to y. And think on this guy, how does the derivative with respect to the derivative to gamma I? So this was a coordinate, so therefore this is the associated vector field. How does this guy change coordinates? How does this guy change coordinates? And you will find out that this guy changes coordinates exactly, precisely with this change of coordinates. And this is the meaning of why this appears. So I'll give exercise 3 because I don't want to talk about these things, but an easier way of finding all of these changes is by including supersymmetry. So let me tell you what is supersymmetry in this setting. So this is the algebra, essentially an infinite dimensional version of what Rickard was talking about. I just told you that Virasoro was this. It is just simply generated by one guy over 12. See? So I'll add an odd guy now, the generator of odd supersymmetry. Well, I should tell you first that is of conformal weight 3/2. So this just means this. G is odd. This is a Fermi. And the bracket of G with G gives you F. Someone knows the OBE of G? Hopefully there's no one there to check whether or not I'm wrong. I think that's correct. I'm struggling to get wrong the n equals 3. But this is called the Neveu-Schwarz algebra, or the n equals 1 supersymmetric superconformal algebra. Whenever you have this structure on a vertex algebra, you can define, so, definition. A conformal structure on a vertex algebra is, on a vertex algebra V, is an embedding of Virasoro. So it's a vector, just L inside of V, is one vector that satisfies these commutation relations, that satisfies star. So this means it commutes like Virasoro, plus one extra condition. We have an endomorphism of V, which is grab your L, take lambda brackets with whatever vector, and put lambda is equal to 0. So this is what you guys would call L minus 1. So this is an endomorphism of V. And I want this guy to be the derivative in the vertical. So that endomorphism is if you trace back all the definition of the lambda bracket, this is what you would call L minus 1. Okay, so this is a conformal structure. So let me tell you what is a supersymmetry. A superconformal structure is a G satisfying this. And for free, you get an odd endomorphism. For free, you get an endomorphism T that is just the same thing. It's just you take G, you take lambda bracket, and you put lambda is equal to 0. And this guy is a square root of your ddz. This is exactly the derivative that Rickard was talking today. D squared is equal to D. So once you have this, I can collect my fields, BC's beta gammas, in just two fields. I could have been even fancier and collect the 4 of them in one. But 2 is going to be enough. So I could collect my fields into some big field, which is just going to be only the coordinates gamma i's plus some theta times D. Now, yeah, so my superfields are going to be this plus some theta D of gamma I. D of gamma I is going to be Ci. And some, I don't know how to call this guy. S. I don't know, for some reason you like S. S, which is the vector field Vi plus theta beta I. And if you work with superfields, you only need this. You don't need these two guys. So you only need these two fields and this operator D. So now exercise. Exercise. S and phi commute as just 1. So S lambda phi is equal to 1, and they change. S and phi change as vector fields d by d gamma, and this as gamma coordinates. So you don't need to care about these transformation properties of the vector. Okay, so we're done with exercises. Let's move on to geometry. So what is the actual? What is the theorem that you've proved. If you come up with these local systems in each patch, you prove the following theorem. On any manifold X, there exists a sheaf of vertex algebras. Called the Cattaneo complex of X.
Why vertex, not super?
Yeah, so I don't like the word super. I think it's just a mathematicians trying to be fancy. Everything is naturally super. So there's a naturally vertex algebra called the Cattaneo complex of X, which locally looks like a B, C, beta gamma system. It might sound very, very stupid, but let's think a little bit on what structure this sheaf sees on the manifold. Okay? So in particular, if you have this, if your manifold is compact, for example, if X is compact, then we've associated a nice vertex algebra, which is just the cohomology on X of this sheaf. So this is a natural way of giving me a vertex algebra out of any manifold. And the question is, in as much as if you give me a manifold, I can give you an algebra, I can give you a range. Just take the Durand cohomology. What structure of the manifold this vertex algebra captures? What geometric structure on X gets captured in the algebraic structure of this vertex algebra? Alright, so let's do that.
X is a complex manifold.
That's a good question. So X is in any category you want. So if X is smooth, it needs to be smooth. This BCs and beta gammas were defined in terms of differentiable function. But if X is an algebraic variety, then I'm going to think of this as a sheaf of holomorphic vertex algebra. If X is smooth, you're going to get a sheaf in the smooth category. Most of the literature, and I think this is an unfortunate situation, thinks of the Cattaneo in the holomorphic setting. And they claim, for example, that this is the Cattaneo part of the half-twisted sigma model. Maxim and me, we take a different approach. We look in the smooth setting, and we think of this as a full sigma model, just in the Hamiltonian setup. So these two things need to be matched up at some point. All right. But I'm here to tell you what algebraic properties that vertex algebra there has. So first of all, this is a deformation of the algebra. So this is a quantization. This is a quantization. And this already is an incredible result. This is a quantization of the Poisson vertex algebra associated to what I just told you is T2 of T star 1. Well, I should probably look at this. Maybe some better. Of X. It is the Poisson vertex algebra. It's a quantization of this Poisson vertex algebra. The beauty of this result is the following. This Poisson vertex algebra, remember, this was built out of geometric data, vector bundles. So I can tell you explicitly how this guy behaved as a vector space. So let me tell you what is this guy. So this guy, it has a gradation by vector bundles on X. It's a beast, it's an enormous beast, but you know this beast. So this P is going to be given you as follows. I'll obtain this in two different ways. But let's start with this way. So this is as follows. You start with T star of X. And now take the... Okay, I'm going to use this notation, which I think is wrong, but it's not. So I'll take the wedge power of... So this is the RAM differential forms on X. Okay? And I'll take the tensor product with polyvector fields on X. And I'll take the tensor product with the symmetric algebra on T star of X. And I'll take the symmetric product with symmetric algebra on T of X. So let me tell you where everything lives. Right? Since we're at the classical level, there's no fancy change of coordinates. So this, let's start here. T star of X, these are the fields CIs. These here are the fields BIs. These are my fermions. Here, I see my bosons. So I'll put here del gamma I. And here, I'll put my other bosons, which are my beta i's. So now I'm going to give you a grading on this bond. Now I'm going to give you a grading on this bond. Okay? So, first of all, charge. Let's charge these guys. The bosons would have charge 0. So this will have charge 0. But the fermions, I'll give them a grading. I'll give charge 1 and charge minus 1 here. To the generator. So a 2-form will have charge 2, and a bivector will have charge minus 2. And now let's give him some energy. I'll give conformal weights, the ones that you know. I'll topologically twist this. I'll give these two guys, I'll give them conformal weight 1. And these two guys, I'll give this conformal weight 0 to differential forms and 1 to vector fields. Now, my answer actually has much more. It has all the derivatives of these fields. So instead of 0, 1, etc., I'm going to put k plus 1 to denote how many derivatives I'm using. K plus 1 and k plus 1. And now I'm going to take the tensor product over all k. And I'll call this the elliptic genus of X. So this is a huge tensor bundle. This is a bi-graded bundle. So this is bi-graded. So this is a direct sum of kj of Lkj, where k is the conformal weight k part and j is the charge j part. And each one of these guys is a finite rank. Okay, I don't want to say much more about this because I'll just talk about this next week. But let me tell you how this comes up in Cattaneo land. Okay, so let's start constructing sections. So global sections. And here you see what the problem is. The problem is the following. Suppose I want to give you a section of a vector bundle. What do? I tell you the section in an open set, I give you a section in another open set, change coordinates and they match up. But my problem is that when I change coordinates, so let's suppose I want to give you a change of coordinate, a section like this. Let's say you have an endomorphism of the tangent bundle, right? Pick a complex structure on X. Suppose I is a complex structure on X. Okay? So I think Richard was writing this as IJK. So what is the natural object that will associate in a local system of coordinates to this guy? I'll just give you IJK. This depends on the coordinates, gammas. And now I will contract with the natural objects. BK changes as a vector field and CJ changes as a differential function. So now I need to tell you, okay, so when I change coordinates, I want this field to behave in the same way. I want this to be a global section. Certainly, this is a global section of this vector bundle. And this locally is a section of the vertex algebra. But when I change coordinates, this nasty beast here is not even associative. I need to tell you how do I change coordinates. I need to tell you how do I write the brackets. So I'll write them like this. Let's change coordinates. So this guy here will pick up a couple of derivatives. I'm not going to write this, of course. Right? So this guy will pick up some derivatives like this, and here's some gamma tildes, and some gammas, and some gamma. And then here you have your I. So that's this guy. This guy here will have some del gamma that I just want to show where the complication will come. And here we'll have some del gamma C. Right? So this C is going to have the del tilde there, and this will have the del tilde there. And now I want to check if this is equal to that. If I am on an associative algebra, this is easy. Just pull those guys out, cancel with these two derivatives, and I get the same expression as before. And this is how we construct global sections of vector bundles. But the Cattaneo complex is does not consist of vector bundles. The multiplication is not associative. So when I pull back these guys to cancel these derivatives here, I pick the non-associativity terms, the associators, and I do not contrast them with this expression. So how do I solve that problem? I choose a connection. And this is a quantum correction in your language. So I will choose a connection. I'll just write down the critical symbol for this connection. Oops, I got myself into trouble now. So let's see how is the connection. So let's see if we get the correction correctly. I, J, K. I will contract this with I, J, and I will add here del gamma K. And now this solves the problem of the non-associativity. So this is not a section of caragram, and this is not a section of this is not a tensor. The Christoffel symbols change with an inhomogeneous term. And the inhomogeneous term that these Christoffel symbols add cancels exactly the associator that the horrible thing in the caragram complex has. So this is the first stage where you realize that constructing sections of the caragram complex is complicated. Therefore, existence of nice tensors on my manifold should give me nice algebras, nice algebraic structure on the vertex algebras, on the caragram complex. So let me give you a theorem.
Here I is the complex structure.
Yeah, actually, for this guy to be globally defined, the only thing I need is for this guy to be globally defined, the way I'm writing it here.
This complex structure is holomorphic form.
No, wait. No, for the section to be well defined, there's nothing. So any endomorphism of the tangent bundle would produce a section. Shit. Let me make a statement that I'm not sure if I have correctly now. No. So no, I'm lying. Let me Maxim is right. So for J to be well defined, so J doesn't need to be a complex structure. I doesn't need to be a complex structure, but for I, J, K, well, for that section J that I wrote there, being well defined, globally, you need C1 of Tx to be true. Sorry?
Is that P1 or C1?
C1. The first term class of Tx to be true.
So you're saying that in the case of CP1 is not well defined for the J?
Sorry?
In the case of CP1, you're saying it's
this J will not be a global section of the caragram complex. So this is already the example.
But carried around complex makes sense.
The sheaf makes sense.
Yes.
And the local sections is huge. It's the full free system. But the global sections are not. So you see here where we added interactions by just gluing things. So the existence of this conformal structure, for example, will really depend on the manifold. So let me add some stuff. Actually, I might want to retract this later, but let me tell you exactly what the result is, which is a theorem. And the theorem certainly will need this. So theorem. X is a smooth manifold, so X in the smooth category. Smooth category. So caragram is in the smooth side. Let I be a complex structure. Be a complex structure. Let G be a Hermitian metric. And let omega be the corresponding Kähler structure.
Kähler form.
Okay.
Kähler structure in some sense.
Okay. Be the corresponding Kähler form. So to each one of these guys, I will associate 3 sections of the caragram complex. I will each one of these generate a section, a global section of CDR. I'll spell this out in a second, but the point is that to geometric data, in the way as here, so this was more or less the story. You start with the obvious tensor that you would put, because you have local tensors, and then you correct them enough so that you can glue this in patches. And you can do this for any tensor on your manifold, as long as the tensor is holonomy invariant. This is going to be the statement. So if you start with these three things, then you can construct global sections of the Calabran complex, and theorem, the vertex algebra of X, CDR, has, so these two sections has an embedding of two different Virasoros, two commuting Virasoros. Exactly what you would want in physics. Of two commuting Virasoros. L1, L2 of central charge sim is equal to 3/2 the dimension of X, if and only if the Ricci curvature of G is 0. So if you give me a Taylor manifold, yes?
Yeah, I just have a question. So there's this Calabran complex. Is it a complex or at the moment it's just?
It's a very bad name.
No, good. So yes, so I'll give you the complex. Give me 2 minutes and I'll give you the complex.
Yeah, so when you're taking cohomology here, you're not.
It's shift cohomology of X.
Not total cohomology.
This is shift cohomology. Yeah, the total cohomology is going to be the round cohomology.
Okay.
So this shift cohomology is going to give me a vertex algebra that itself is a complex. But I want to tell you why the vertex algebra is a complex only in this particular case.
But in fact, it's very misleading name. I mean, when you say about it, I mean, you shouldn't use the words complex, right? It's just shift of SUSY vertex algebras. But the name got stuck and then...
No, but I think somehow this is important in physics because the complex name here comes from the BRST differential.
No, right, but it's...
The differential here is going to be the BRST differential.
Right, but what we call CDR is...
Yeah. Completely. But let me stress this theorem. First of all, this is different than what happens in physics, and Maxim has been fighting about this. This is a theorem, and this vertex algebra carries two Virasoros of the right central charge, if and only if the Ricci metric is, if the flat is Ricci, if the metric is Ricci flat. This is already different than what happens in physics. In physics, you do expect to have two Virasoros of that central charge, but when the manifold is Galileo, so this in particular implies C1 of T is equal to 0, but you choose a metric that is not Ricci flat. I'm not going to get into that. But what I do want to say is the following, is that actually these two vertex algebras is more. So Calabran, so the global cohomology of CDR has two commuting copies of the n equals 2 vertex algebra. So this is what you call n equals 2, 2. You have two commuting copies of n equals 2 with this central charge. If you're in this situation. So let me tell you more or less what are these generators of this. I need to tell you what is the n equals 2 vertex algebra. So, okay, so I already told you what n and g was. So what I will do is I will write, so this was the n equals 1 vertex algebra. I will write this g as g plus g minus. And I'm not going to write, of course, this whole thing, but the n equals 2 vertex algebra is a vertex algebra with 4 generators, L, P plus, G minus. These are conformal weight 3/2. This has central charge 3 times 3/2 the dimension of X. And there's an extra U1 current, J. So U1 current means J is equal to 1. This has conformal weight 1. So, what's going on? This guy is associated to the complex structure. These two guys are associated to del and del bar. And this is associated to the Laplacian. kind of. But I have two commuting copies of that vertex algebra. So now let me tell you what is the complex. To tell you what is the complex, I'll do this in the holomorphic setting. Okay? So I can do two things. What physicists do is the following. If you have two commuting copies, so I'll say this for physics. So let's say I have an N plus and an N minus. So I have a plus sector and a left moving sector. Let's call this, yeah, left, 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 and a right moving sector. When you have an N equals 2 structure, you can topologically choose one of those and take cohomology, BRST cohomology. So you kill one of the two N equals 2 structures. If you do so in this situation, you will still get a vertex algebra. So if you take the BRST cohomology for Q, say right, you are led to the chiral complex holomorphic. To the total cohomology of the chiral complex, which is purely holomorphic. This was Witten observation when he talked about the 2,0 half twisted sigma model. So he observed this statement. It's just that the way that you find this is very, very twisted. In any case, so now I'll restrict to only the holomorphic part. If I only look at the holomorphic part, I have one copy of N equals 2,2, but I have it already topologically twisted. So on the chiral complex of a holomorphic manifold, I have a Virasoro of central charge 0, a QBRST that now is the left QBRST that survived, another fermion of conformal weight 3/2, and a U1 current. This is the U1 current on the left. So this structure is there on the chiral complex. So your BRST differential, the complex is as follows. This U1 charge locally is counting how many bosons, CIs I have, BIs. Now I need to be careful, I am in a holomorphic coordinate, so this should be C alpha, B alphas. And this has charge 1 and this has charge -1. And the J0 counts this charge. And the Q increases charge by 1. The Q0 increases charge by 1. So, okay, let me tell you the theorem, which is the important theorem. Whenever you're in this situation on Galileo, you have this vertex algebra. Remember I defined these operators. Let me define this other operator. So we have this relation of vertex algebra with this operator formalism. So I have this Ln z to the -2 minus n. In particular, I have an operator which is L0. The same for the J. If I take my field associated to J, I have the sum of Jn z to the -1 minus n. And in particular, I have the operator J0. And I have my infinite dimensional vector space this. That apparently this has nothing to do with physics. I constructed without ever writing an action. I never ever wrote an action for this system. I locally constructed a BC betagonal system. I constructed an N equals 2 of the right central charge for you. And now I can do the following, which is what you do, which is what is the trace, or the super trace because it's a super vector space, on the full cohomology of X, chiral gram of X, of the operator Q to the L0, Y to the J0. I'll fix this in a second. I'll just, oh no, that's correct. I need to be careful. No, I think I'm just going to add a Y to the minus the dimension of X over 2. And this is also going to go L QY, and this is equal to the, I had already defined, remember that we had, yeah, probably this, remember that we had a vector bundle, L, which was a sum of L QY. So this is equal to the sum of -1 to the I, Q to the J. I'm sorry, JK, I think I wrote here. So let's write Q to the K, Y to the J, times the dimension of HI of X with coefficients in that bundle. And I'll fix this also by the minus the dimension of x over 2. So this is a very important statement. The Cattaneo complex produces the same partition function that you guys are used to see. This is a two-variable elliptic genus of a Galileo member. Two-variable. Of x. This is a holomorphic function on q and y. If you write this q as e to the 2 pi I tau and y as e to the 2 pi I x, this converges in the upper half plane for tau and the plane for x. And its modular invariant in a sense is a weak Jacobi form of weight 0 and index the dimension of x over 2. I don't want to get there. But the thing is that the Cattaneo complex sees this explicitly, and in particular it tells you that the full elliptic genus, the vector bundle, was a classical version of a vertex operator algebra. Because I got this elliptic genus, this bundle, I got it by looking at the Poisson vertex algebra, not at the vertex algebra. So CDR, this homology of X of CDR, has a filtration, Fi, such that the associated gradient is this elliptic genus. In particular, if you're looking for algebraic, the elliptic genus, you can think of it as a limit of a vertex algebra. You might look for actions on the elliptic genus by looking at vertex operator algebra actions there. Okay, so I'll have a few minutes, so I want to tell you a program. So I want to tell you similarities between this Cattaneo complex for T and then for Courant algebras. So first of all, if X is n equals if X is Galileo, I just said the Cattaneo complex. I should say this because I think all of these symmetries were invented by people that are in this order. If X is Galileo, then Cattaneo complex has n equals 2,2. If X is hypercalar, then Cattaneo complex has n equals 4,4. If X is, I think some student of Maxim managed to, so if it's a Galileo threefold, it also has this Odaki algebra construction, which is by adding the field that corresponds to the holomorphic point form. In all of these cases, you have an n equals 1,1 structure because it is smaller, but this you cannot prove. If X is Riemannian, we're hoping to get n equals 1,1, and we can't prove this. This is a very hard problem.
Not for general Riemannian, come on.
Sorry?
Not for general Riemannian, you will get conditions in the natural.
That's correct, but I want, on a manifold that is not Galileo, I want to find an n equals 1,1. We had an equal 1,1 symmetry without asking for a complex structure, for example, right?
Yeah, but I mean, you're not saying Caylor, you're saying Galileo.
Yeah, that's right.
There might be something similar here.
So on Caylor, no, not even on Caylor, I cannot produce on Caylor an n equals 1,1. So, okay, so.
No, I'm saying there's some additional condition which is not.
Right, no. There might be quantum conditions to this node. The question is Riemannian plus what? I want to see n equals 1. No, sure. But I don't know what this, I don't know how to produce a 1. So the thing is the following. So perhaps this will clarify things. So if you look at the n equals 1 structure, n equals 2 structure, if you give me the current and the generator of supersymmetry, you obtain the pool n equals 2. So the current is easy to construct because that's it to a complex structure. But the stress energy tensor is impossible to construct. I can only derive it from the current. So this is why I cannot construct an equals 1,1 structure. But what is surprising is these other things. If X is spin 7 or G2, we know at the classical level that these have the right supersymmetry. This is papers of Zabzine and Papa. They did this for them. So it's interesting, this statement. So at the classical level, in the flat space, this was done by Papadopoulos. At the quantum level in the flat case, this was done by Zabzine and above. At the classical level in the curved space, we managed to do this with some students of Domenico, Yul Ekström and Johan Schelien. And now Lazaro here is working at the quantum level in G2 and has a promising structure related to what's associated with submanifolds. So the question is, okay, so why? If Cattaneo complex sees the same supersymmetries that physicists are hoping to get in the quantum level, so what is the connection between these two things?
So when it's P7 on G2, what kind of supersymmetry?
It's complicated because these algebras are Hamiltonian reductions, so all of these algebras are quantum Hamiltonian reduction of super Lie algebras. So I can tell you what those super Lie algebras are. So this is SL1, is this correct, SL1? So this is SO43, SPO43. This is SPO32. This I know is SPO21. There are Hamiltonian reduction of this. These are called W algebras.
And is there any, I mean, I don't know, is there any kind of guess relation between the kind of special holonomy you have and...
I was hoping someone would ask me this when I finished, but I arrived to the US about 10 years ago, probably more, and there was a thesis defense by Alberto de Sole, and he gave the following list. He said, let's classify vertex algebras generated in degree 1 and 3 halves. The degree 1 part every physicist knows this is a current algebra. The degree 3 halves is going to be a modulo for this current algebra. Let's classify when the pairs are irreducible and the module is, the pair is simple and irreducible. This list happened to be exactly Berger's list of special holonomials.
Wow.
There's this other list of W algebras. The W algebras are n equals 2, n equals 4, n equals 1, spins, bajas, and Zabzine. And there's a third list, which are the super Lie algebras that produce these guys. I've been 11 years trying to think of this problem. I don't know. All right, so let me tell you in the last 2 minutes what is the statement I wanted to make regarding the electrogenics.
You screwed up the name of Shatashvili.
Oh, okay. There's no way.
You're lucky that he's not here.
Yeah, no, there's no way I'm gonna write those names correct. My work with Jesse also. No, I'm forgetting what is the statement I wanted to make. Oh, okay, so the other problem is as follows. If you start with a current algebra, an arbitrary current algebra Domenico, for example, if you start with K, so let me make this statement, because this statement is interesting. So if you start with, so E is a current algebra over this. Remember when this was a point, this was just a Lie algebra, and we can choose an arbitrary basis here. Let's choose dual basis for this Lie algebra. In a current algebra, you can also do this. You can choose global sections that are dual with respect to the natural pairing of the current algebra. So write the Casimir element, which is exactly what we wrote for the Villasol. So this now, locally, you chose the sections of the current algebra. Locally, this gives you a section of Carrel round. This section exists globally if and only if. This section exists globally if and only if your current algebra can be written as L plus L star with the determinant of L having, well, being triggered. Oh, I guess I should do this. C1 of L being 0. But in that case, this guy gives you a Villasol. So if you want to get the super partner of this, what you would do is you would write the cubic Dirac operator for the Lie algebra. So if you think of a current algebra as a Lie algebra or a manifold, here's another question. Write all the higher Casimers for this Lie algebra. Do they generate a nice geometric vertex algebra structure on the manifold X? I don't know. But when the manifold X is a point and the current algebra is just a Lie algebra, yes, this is the W algebra. Again. Classical level. Okay.
Questions?
Yeah.
Can we construct the always BRC charge from the
Yeah, so yeah, I failed to say this. So the four fields, the 4 n equals 2 doesn't exist always, but their zero modes do. So if you, when you change coordinates, this non-associativity, all of these axioms that I wrote for the failure of associativity or commutativity, failed by a total derivative. So whatever those failures produce would be killed at the zero mode level. So you always have the complex, you always have the BRST charge. You can always topologically twist these models.
So from physics construction of big gamma system, there's not just the gluing of the coordinate, but you could also glue along the worksheet side. Do you have some?
Yeah, so that part is easy. This part is understood mathematically. So the gluing is more like the kind of things that Nick might talk. So I'm describing you a vertex algebra, and I refused to talk about these coordinates of the field, this z that I wrote in the end. So the gluing that you're referring to would correspond to change coordinates in this z. So this is a procedure that is, in mathematics there's a difference between vertex algebra and chiral algebra. Vertex algebra is something that is a vector space with some structure. A chiral algebra, you need to give it to me on a curve. In particular, this chiral run complex produces you a vertex algebra on any Riemann surface of any genus, on any super Riemann surface of any genus. This actually produces you vector bundles on the moduli space of supercurves.
There is some obstruction, for example, C1 with this product.
No, so the subtraction is for this vertex algebra to be superconformal, to have this n equals 2 structure, but the vertex algebra exists always.
No, there is a C1 times C1. C1 of the source times C1 of the product. Just to take it to be.
No, again, this is because you're insisting in having a Virasoro. I don't care about this. So this vertex algebra exists for any manifold. So I mentioned this product that Witten produced. I'm telling you the fold. This is a theorem. You give me any manifold, I'm giving you a vertex algebra. Here's another theorem. You give me a vertex algebra, I give you a chiral algebra over any curve. So the thing is that these vertex algebras might not have an action of the full Virasoro. And this is something that physicists want. They want to have a stress energy tensor. But my definition of vertex algebra did not include a stress energy tensor.
Yeah, well, we'll hear about it next focus week. Any further questions? Okay, if not, let's say. So I remind you that next week there will be a conference and we'll start at 9:30, not at 10.